Okay, guys, so today I would like to talk about the electric field. And before I go there, I'm going to go very quickly I'm going to explain about the concept of field. So every time we talked about field, right, it's very easy concept. Field is just a region of space for which each point in space you associate a quantity. Okay, in this case, for example, if you think here in this, I put this here, right? This plane, the 2D plane. Maybe make this clearer. I can put here the plane, and for each region, right? For each point in this region of space represented in this plane, we we associated a number. I put some random numbers here because this is not supposed to be great. It's just for you to understand that what field means. You have two types of fields, right, in mathematics. This one that you associating just a number to a point, to every point in space, certain quantity represented by a number, right? You can use, even sometimes you can see, for example, like a color code to represent like scalar like fields. And but you can use also vectors, right, to represent those fields. So fields in general, they are divided in two major types. One that you we call like scalar field, and the other one that we call like a vector field. And we already studied one kind of vector, very famous vector field that we studied in physics B, I think, or physics A. I'm not exactly sure. That is the gravitational field, right? So you are familiar with this idea. So instead of just a number for each point of space, right? For each point space, now you have like a vector. You assign a vector for every single point in space around, like in this case here, the mass. That's we use this technique to calculate the gravitational attraction masses. This concept, guys, was introduced by Michael Faraday. Was like a He's very admirable like scientist. He invented many things. He discovered many things, and the main one of his major contributions was about like this idea of fields. And of course, guys, in physics, I just explained to you, right, generally in terms of mathematics, right? But in physics, every time you associate this number or this vector is going to be associated to some physical property. Okay, so this quantity is always going to be associated with this physical property. So what now comes to the present class? We are going to talk about the electric field. What is that? Remember, let's go back just a little bit and remember what you are trying to solve here. What exactly you are trying to quantify. What exactly we are trying to find, to determine. Remember, guys, we are trying, every time we have charged particles or a group, right, of particles, we are interested here in calculating the forces, right? So this is the main point here, the main goal of this class. We are trying to find the forces that are acting on those particles. And the first technique that we use to solve that, to find to find these forces, was the Coulomb's uh, formal formal modeling the forces between charged particles. Today we are going to use another technique. The electric field is just another technique to find exactly the same thing. Instead of now considering, for example, these two particles, we think about this problem as one isolated particle, and this particle is modifying the space around it. And the way it modifies is through what we call the electric field. And the electric field is we associated, right, this one amount of electric force per unit of charge in that particular point in space. Of course, here I put only in one direction, right? But this is valid for every single point in space. You are going to have like a particular electric field. This concept is valid for every single, let's see, this we call this point 1. If you have like a point 2 here and so on, you are going to have like a oh my god, my drawings are try to make, let's change colors a little bit. Let's put here, let's say if I have a point here, if I have a point here, I'm only representing in 2 dimensions, but this is a 3-dimensional effect. The field is really 3-dimensional phenomenon. So you have one, for example, the electrical field here, electrical field is acting here, right? This is, of course, this is not in scale. I'm going to show later. If I was to be accurate, the length of this arrow should be proportional to the strength of the electric field. But I'm not putting this here now. Just to make for you to understand that this is 3-dimensional phenomenon. Let's call this point 1, this point 1. Well, the units, right, of electric field are Newton per Coulomb. Sometimes you're going to see this represent like this, Newton the -1. This is very common for scientific papers. And what is the advantage actually of using this approach? Well, the main advantage here of using this approach is actually you are going to have, for every single point in space, you are going to have assigned a certain value of force per coulomb. So that means for any kind of charge that you put there, is very easy to calculate the electric force, right? For example, let's think that if you have here this charge, right, the arbitrary charge Q, like BQ, and this charge is generating an electric field with a strength of 10 Newton per coulombs in a certain point of space. If, for example, if you put like a charge of 2 coulombs in this point of space, right, same point in space, you're going to generate a force that is 20 newtons that I represent here in with this vector here. So this is going to be 20 newtons force. On the other hand, if now instead of these 2 coulombs charge, you put like a charge of 2 coulomb, a 4 coulomb here, you are going, it's very easy to calculate here. You're going to find that the force now is going to be 40. Now you can see that actually is simplified, right, guys? This is not so obvious when you are dealing with, for example, with a system with only one particle, right? It's going to be more obvious when you deal with problems with more particles, right? Multiple particles problems. For example, this case here, right? For this case, you have like 4 charges and you are interested in the electric force that all the charges 1, 2, and 3 are going to generate here on this particle. Then I'm going to call this Q0 here. Remember, the process here was actually to calculate individually each one of the forces. So you are going to calculate here the force of this the particle 1 generates on this particle 0, and then you calculate here the force of the particle 2, and then here you calculate the force generated on particle 0 because of particle 3, and so on. And after this, you apply the principle of superposition, and then you are going to the net force on this particle. But what is the main problem here? Okay, we can do this also geometrically, right? You just have to you can, okay, solve this graphically. You have here, so the resultant for this guy. And place the vector here. Okay, and the resultant here is going to, let's put color, let's put resultant is the net force in this. But what we did here, what is the main point, right? This we learned this in the first two lectures, right? So this is the net force here that we learned to calculate, you right, vectorial calculus and so on. But man, this method, right, the electric force that you are going to find for this charge at this particular point in space is only valid for this particular charge, Q0, right? So that's the main point. The main point here. If instead of using this approach, right, the approach where you calculate the force directly and then you add you make some vectorial addition, and then you find the net force. This is going to be, sometimes it's very complicated. This is going to be simplified if what we do is actually calculating, right, the electric field for this particular point in space, guys, the same way like you are used to do, right? Like summing, adding up like vectors. We can do this here too, using graphically solving this problem. Same way like you did before. Here, here, red, vector, and then the result is a net electric field. And the main advantage here, my friends, is actually this is valid for any charge that you place in this point in space. All you have to do to find the electric force here, right, is just have to multiply by the electric field, and then voila, you have the electric force. So this is very important difference, right? So this is, we have like a simplification of the whole process of calculating the forces, right? The main point here is that this is valid for all for any arbitrary charge that you place there. And all you have to do to calculate the net force is actually you have to multiply This arbitrary, we call, I'm calling this arbitrary, but physicists, we call this actually test charge. And as long, very important, we have only one limitation here, guys. One small limitation here. Okay, as long, all you need, right, for this to work is actually for this charge here, the test charge, to be small. Of course, the charge of the on the test charge should be smaller than the other charges, because if you put like a charge with a very high charge inside this configuration here on the right side of our screen, so this is going to scatter, you can actually scatter all the other charges, right? So that's why we try, the only limitation here is actually to charge not this. Did you understand until now? Do you have any questions until now? I'm going a little bit fast here. Just to make a comparison here, guys. Remember, so this is not strange for us, unfamiliar. This is actually familiar, since we saw this already in physics B, right? Remember that the gravitational force is actually the gravitational constant multiplied by the product of the two masses and divided by the square distance between the two masses, right? Those are similar, we already know that they have same mathematical formula, the same mathematical formulation. And here we knew also that the gravitational field was this gravitational force divided mass. And we already use the same concept, right? You don't have to consider a mass to calculate the gravitational field in any point of space. Calculate using the planets, for example. If you have one object kind of body like orbiting around this planet, it's easy to calculate the gravitational forces just applying the concept, the gravitational field. We are going to apply the same, exactly the same principle here. Okay, let's go up and let's talk a little bit about that, because as I mentioned before, like the electrical field is a vector field, right? So that means we don't have like a distribution of numbers in space. We are going to have like a distribution of vectors in space, and this can be very complicated. Let's look at this one. Can you guys see me my screen here? Simulation, can you see this simulation? My computer is very slow this morning. But look, so this is very, as you can see, very complicated. Of course, the electrical field is continuous distribution. I cannot represent every single vector here because it would be impossible to understand. Just representing vectors in some points in space. And as you can see, the first thing that we notice is actually, of course, the electrical field is a three-dimensional phenomenon, and this is going to have like a three-dimensional representation. But what is most common is actually representing this as a in perspective. Right? You represent like a cross section, or you represent a projection. Generally, this is what we do to understand better to represent graphically the electric field. We simplify, right? But even simplifying, you can see that it's very complicated, right? You can see here one representation where, of course, every time, for example, if you are trying to represent the vector field of for this particular charge here, we have, let's put in orange since the drawing. You have the electrical, let's call this point 1 and this. So the electrical field here for this point and the electrical field point. The electrical field strength in point 1 is actually bigger, greater than the electrical field in point 2, because of course, because of the length of this arrow represent the magnitude of the vector, right? This is very important, this representation. But as you can see, this is, even though we simplify, right, from a 3D, three-dimensional representation here to a 2D projection or cross section, right? We simplify here, and we can. It's still kind of complicated, right? I'm neglecting some of the points here, right? You have like vectors everywhere here. Since points in space, they are not, even though this drawing here is a discrete distribution, like for real, this is not discrete, this is continuous distribution. We have like all distributions around this charge here in space. Be very complicated. Now let's think that actually you are representing not one particle, but you are representing two particles, right? Like the one I'm showing here in this. If I have here, oh, right here, see, if you have like two particles, my friend, in this, you wanted to represent the vector field, the electric field for two particles. Wow, starting getting very, very complicated. If I put one more charge here, here. Oh, let's put two same. Let's 24. 24 long. As you can see, starting getting very, very complicated to understand what is going on and how to apply very easy, simple, very, very easy and powerful principles like this principle, right? For this kind of cases where you have more particles involved. And here again, here I'm just representing like a 2D presentation of the real phenomenon that is actually three-dimensional. So what to do? What can we do to solve this kind of problems? Right? This can become very complicated to solve. So the main idea actually is to use the idea. This was Michael Faraday like idea, is to represent the electric field as lines. And this is very, you just have to stick, you just have to adhere, you just have to comply to a certain set of rules for drawing the electric field lines, and they all make sense. So I'm going to explain briefly here the rules that we have to draw the electric field lines. First of all, guys, the electric field lines, they have only two options for them. They originate in a charge, or they converge to a charge. If this is by convention, okay, if the charge is positive, like this one in red here, if the charge is positive, the electric field lines are divergent, so they go away from the positive charge. If the electric charge is negative, so the electric field lines are going to converge to this charge. Okay, my friends, so that means in either way, some people say, for example, for positive charge, that the lines, they start at the charge and they end in infinity, and for the negative charge is the opposite, they start in and then converge to the charge. Okay, let's go. Always remember that. The second rule that we have is actually the number of field lines is proportional to the charge. People are going to say, oh, but come on, the lines are not supposed to be discrete, right? Actually, you know that the electric field is continuous, but we don't need to represent all the lines. That's the main point here. Okay, going back to this rule, that means that the number of field lines that we have is proportional to the charge. If you have, for example, here I put like, for example, this charge is double this one, the charge here. Let's say if I call this Q1 and I call this Q2, this Q2 is double twice the charge 1 to 1, and that means that the number of lines are going to double too. So the number of lines clearly is directly proportional to the magnitude of the charge. That's a very important rule that you have respect. Another one, my friends, always at every single point in space, right, the electric field is going to be always is going to be tangent. The electric field is tangential to the field line at that same point. Of course, the length of this arrow here, the length of the vector is proportional, right? Remember, length of air at the point of the chart. Remember that. Let's go to the next lines, my friends, is if you analyze, if you check like two surfaces, right, in space here, you see that clearly this surface S and this surface S prime, if the line density is higher in this surface, the density is representative of the electric field for that region in space. That means if you have more lines over a certain surface, the strength, right, the magnitude of this electric field is going to be higher. That's all. Very easy. Here you can see, you can even count in this case here, right? You have like this smaller surface, you have more lines crossing over. That means that you have more strength of this electrical field here, this region of space here, actually greater than the electric field in this region. The same like analyzing, let's go back one page. The same here, right? If you analyze, for example, one surface here between these two charges, right? If you analyze like a surface here and one here, and you call this electrical field in this region in space here, this region in space, call the first one sub 1 and the second one is sub 2. Clearly, by convention, right, by our rules, the electric field region 1 is greater than electric field in region 2. And okay, another rule, my friends. Okay, the last rule. The field lines, they never cross. Doesn't matter what happens. I put a video, right? I included a video in the Wiley material. In the video, people are going to show some experiments, and you can actually, and they use some techniques to visualize the real electric fields. And as you're going to notice, they never cross. Doesn't matter. And so this representation is actually representing graphically what I've just stated. The lines, electric field lines, they will never ever cross. That's very important concept. Okay, let's move on for the next part of this lecture, guys, that is about the superposition principle. Again, following what we observed, Coulomb's law, talking about principle. Again, when you have you are going to use the same here to solve. If you have more than one particle, charged particle, all you have to do, my friends, is actually apply the principle of superposition. You treat how each one of the particles are going to affect that particular point in space, and then after you calculating each one, you just have to add it up, like vectorially adding up all these. Not supposed to be difficult for you. And just remember, in general, what I show you for the first, in the second, in my explanation, this is valid considering that have what I mean here is that actually calculate the forces. We have to consider then the charge of the particle, right? After calculating the net, the net the net to find the final electrical force acting on this particular, on any particular charge, you have to pay attention on the sign, the charge. If the charge is positive, my friends, so the force and the electric field are going to have the same direction. What I'm saying, that if the charge is positive and you have the force is going to have the same direction, like field. If it has like is negative, you're going to have the opposite. Put here graphs for you. See that. Let's I also put some simulation for you. This is course of all those guys doing this brilliant work in the internet. So I'm just put this Antonio de Muro made this simulation here. You can play with two or three charged particles here, my friends. You can actually see what is going to happen with the electric. You can play here certain limits, and you can the you can even this guy even included us and play with that. Putting the lecture notes, you guys play with it. Wow. Okay, finish this part. Have about 1 hour to go. I'm not going into much detail on how to solve problems involving particles. Okay, I'm not so interested on that, because why is that? Because we solve this kind of problems in high school. Okay, so I'm not putting too much effort on that, since this is a major review. Just going to make some comments here. Just give me a moment. For example, I decide to solve this problem here. that is in your textbook. Where is this problem? Give me a second to find. That is very common in high school. You have a particular arrangement of charged particles in a particular region and space, and you want to find the electric field generated by this particular arrangement in a particular point in space. In this case here, you have three particles, right? Particles 1, 2, and 3, and they're located in this particular disposition here. You have they're separated by same distance and so on. We can find this distance, right, from these particles to the point P using Pare's law that I just put here. So those are the distances that you have for this from these particles to this point P. I'm more interested here actually is in teaching you again, just revise how to write what is the main point, what is the most relevant, the most significant step that you have to do to solve this kind of problem. First of all, my guys, you always sketch. Make a sketch here, draw all the vectors, and then it's going to be easy. Okay, let's see this particle 1 here. Going to be okay, and let's see how this particle is going to affect this particular point in space. This particle Q1 is positive, is plus E, so that means that this vector plus E, this is a divergent field. That means that the vector is going to be pointing this, oh my